Yes, indeed. This presentation it's about Acros project. It's a project that it's ending. Hopefully, if everything works fine, that for now it's the case by the end of this year. And here I will be showcasing one of the test cases that we were developing during the last months. As you said, it's on AI-assisted DDoS detection and mitigation on a realistic operator network using the Teraflow SDN controller in this case. And this is a joint effort between three partners of this project consortium, which are the CTTC, UPM, and Telefonica. Then, going ahead with this, so just a bit of scope in Acros. Well, we know that for beyond 5G and 6G infrastructures, automation of many industries is a must. We need to also provide advanced methods and for management of services, expanding systems, and so on. And in Acros, what we are developing is an end-to-end service and management platform for those next generation networks that, well, we are trying to provide improved performance, adaptability, growth, energy efficiency, automation. Uh, all the thing it's being crafted according to the ETSI TFS principles. So we want to provide highly distributed domain level orchestrators that are managed by means of cloud managed multi-domain orchestrators. As I was mentioning, we have a number of test cases. There are ones that are focused on the stakeholder driven zero touch orchestration. Others are more focused on the device driven orchestration. Intelligence-driven orchestration. This is the one of focus for this presentation today. And the last one, it's one that was presented a few weeks ago at ETSI TFS, which is the holistic demonstration of zero-touch orchestration. So going a bit more in the details for this test case 3, in particular, we are focusing on the sub-test case 5, which is on a heavy hitter detection for the zero-touch DDoS prevention. Here the point is that, well, you know that in the networks you might have different kinds of flows. We can generalize quite a lot and assume that we have three. So normal flows, which are regular traffic like web browsing and normal things. We have also cheetah flows. These cheetah flows are something that it's also short in time, but it typically implies some peaks in traffic. So imagine here, for instance, if you want to upload short form videos, TikToks, Reels, whatever, these kind of things that essentially generate a spot in the network. This is something that it's kind of a heavy hitter, but it's not something that it's malicious. I mean, it's something that is expected. What is not expected, let's say, it's big, or might be expected for, I mean, correct large file transfers and video streaming, but in some cases you might need to properly detect and manage because they can be in some cases malicious. So what we try to do here is by means of machine learning techniques, try to differentiate the different kinds of traffic flows. And whenever we identify that one belongs to what we consider a DDoS attack, then we implement mitigation actions to prevent them. So going into the details, the sub-objectives of this particular test case 3.5 is on releasing a network digital twin that is able to emulate realistic operator networks using commercial network operating systems. In this case, we are focusing on Arista EOS. Second point is that we want the framework to run on top of AI-powered modules so that these malicious traffic patterns and the prevention of DDoS attacks is driven by means of AI. The third point is about The scalability, so we want the DDoS detection and mitigation pipeline to be scalable and be able to block the attacks. And finally, we are interested in exploiting as much as possible open source software. So this is the architecture of the solution. As you see here, we have on top left the network digital twin that is based on the Telefónica's mouse world network digital twin. Essentially, this is running on top of the Kubernetes network emulator. So we have a Kubernetes controller, and then we have a number of Kubernetes nodes, and these nodes essentially represent or emulate the different elements of the network. By means of KNE, we can provide the connectivity between the different elements. Then this NDT it's producing traffic flows that are collected and aggregated by means of an aggregation function. This information, then the aggregated flows are provided to the AI inference module that essentially runs a set of already trained machine learning models, and it produces a set of probabilities that the DDoS attack detector filters. So it based on these probabilities, the kind of configured attacks, a set of thresholds, and a set of conditions, it says, okay, this is an attack, or this is just something that I can accept, or based on the policies provided by the operator is acceptable. Then for the selected attacks, a DDoS mitigator executes a logic that I will explain in a minute in order to decide where and which ACL rules needs to be installed to mitigate the DDoS attacks. Okay, so these rules are then provided to the Teraflow SDN controller that it interfaces with the specific devices on the network digital twin to mitigate these specific attacks. Besides that, we have also a monitoring block that is in charge of plotting all the status of all the systems so that we can check that everything is working properly in real time. And the communication of the different elements is done by means of Kafka bus in order to provide scalability and enable that all the components can be replicated and scaled properly. In terms of responsible partners, Telefonica is responsible for the NDT. Then Polytechnic University of Madrid is responsible for all the blocks related to AI, the Kafka bus, and the monitoring engine. And CTTC is responsible for the DDoS detection, mitigation, and the Teraflow. In particular, in terms of deployment, at CTTC, we have the blocks for CTTC, and the rest of elements are running at Telefonica premises to provide also in-out performance in this particular link, especially because you can imagine that this amount of traffic can be huge. Then, about the network digital twin, it has essentially four core elements. The first element are the set of clients that might be benign and malign, so they can just keep generating traffic according to some patterns that we pre-configured. We have then the set of target services and the outside network. We have the transport network itself. And finally, there is one particular router that has firewalling capacities and is the one for the focus in the second part of this demonstration that I will showcase. So here is where we can install the ACL rules. The rest of elements, in this case, we decided not to implement ACL so that we can check that the system properly chooses the right firewall. Phase one. This is the one that was completed by end of last year. So it was somehow demonstrated, and here we are extending this part with the second part of mitigation. Briefly, I will explain that here the machine learning model that we are using is based on the random forest with 20 estimators. It's able to process flows in bulk. That means it can pack a number of aggregated flows and make inference on all of them in order to improve the performance. In terms of some metrics, the training and retraining system takes around 46 seconds to retrain when needed. The inference computation time is in the order of less than 100 milliseconds. It's around 63, something like that in average. And with this model, we are able to process at scale, more or less, the traffic at a rate of around 700 megabit per second. In terms of the model performance, well, I will jump directly to the labels. You see that in the confusion matrix, the true levels and the predicted levels clearly the class identified it's the right one here. In some cases, for sure, as it always happens with machine learning, there are some false positives or or true negatives, let's say, but in general, the classification is done quite well. And in terms of the mapping between the predictions and the ground truth of the different classes, we can see that on top we have the ground truth, so what we inject in the network in traffic as traffic patterns. In the bottom, what the models detect. So you see that they fit quite good. And here I start with the demonstration. This is just the log of the real-time traffic collection. Then we have here in another tab the real-time inference. So you see that it's processing in this case in bulks of 100 and something. It's not the 1,000. It's because it processes. It keeps packing things in a queue, and whenever it has an out, it decides to process. This is the monitoring client. This is the block that feeds the Grafana dashboards and the time series databases with appropriate data for the progress. And this is the dashboard where we can see that the monitoring of all the elements. We see the bytes in, bytes out. We can see the number of packets in, packets out, the heavy hitter statistics, and also the security stats that essentially it's the value between 0 and 1 that decides or identifies if we are under attack or not. Then for the second phase, which is the one that we were developing during this year, this is the part on DDoS detection and mitigation. Now, as promised, I explained here briefly how the DDoS detection and mitigation works. Essentially, we configure the detector with a set of thresholds, and we provide the TerraFlow topology to the DDoS mitigator. Based on that, whenever a new snapshot, which is a pack of end flow predictions, reaches the DDoS detector, the detector checks the probabilities of the different traffic classes, and also takes the metadata to check that everything, well, to identify which are the flows, where the traffic is coming from, and so on. Based on this data, it does the filtering and provides what are considered attack samples to the DDoS mitigator that then, based on the topology, it creates attack models per flow pattern. And based on these attack models, it labels the different elements with the specific flows that are traversing these devices. This information is crucial because then it enables to run this recipe that essentially what it does is to, based on this attack model, compute a Steiner tree that essentially connects the different elements involved in the model. And given that we can specifically imagine here a bigger network, I kept something simple just for illustrative purposes, but imagine that we get in the different elements notification of attacks. Then what we do is we force to include these elements in the Steiner tree, and that way we have a subgraph of the original topology with all the elements that are involved with the minimum connection. So that way we can identify which is the path for the connections, the real one. Even if it's not through SDN that we force the path, with this solution, we should be able to infer which are the paths. Then based on that, we compute which are the closest firewalls where we can apply ACL. So for client 2, we see that it's this firewall, clearly, it's the one that it's closer. But for the client 1, we have routers in front of. So the firewall, that the only one we can use is the one that is just before the server. So we can apply the ACL rule for client 1 over here. Based on that, then we generate the IETF network ACL standardized rules for TerraFlow that are installed on the firewalls by means of GNMI OpenConfig. In terms of the Teraflow architecture, we are using release 6, and in particular, the relevant components are the NBI connector for IETF ACLs, the context database, because we need the topology and the details, and also the SBI connector for GNMI OpenConfig in particular. Well, here I forgot to mention also the IETF, highlight the IETF network, because we need it for reporting the topology. Now here we see a depiction of the network digital twin onboarded in Teraflow. You see, we have here the elements. This particular router here is the one that has ACL capacities, so the one that we use as firewall. We can check here the details of the devices. This is the one with firewall capacities, and initially it's configured with no ACL rule, just the classical routing. Then here we have initially normal traffic in the dashboard for monitoring. So essentially it's this, we have normal traffic, and at some point the attack starts, and we see that the DDoS detector started to identify attacks that are forwarded to the DDoS attack mitigator. You will see here, looking for the pointer. Yeah, here we have the attack that is received by the mitigator, and over here the ACL rule that was composed for this one and is sent. Then here we see that at some point the number of attacks starts to increase, the number of flows that are considered attacks, and we also start blocking these connections. We can check here, for instance, the configuration of this router that has firewalling capacities, and we see that the appropriate ACL rules for blocking the traffic on the specific clients, originated from the specific clients, was created with the specific ports, origin and destination ports, origin and destination addresses. And well, here also, finally, we can check in the Teraflow web UI that in this particular router with the firewalling capacities, the proper ACL rules were installed, and we can see here the specific ones. So, concluding this presentation, we showcase the framework for detecting and mitigating the DDoS attacks proactively. This is based on AI-powered classifiers, and it also provides filtering of non-relevant samples. And for the relevant samples, we create these attack models and generate the appropriate ACLs for the mitigation. All this is based on a realistic network digital twin, based on open source software, well, except the commercial network operating systems, in this case, that we use the Arista CIOs, as I was mentioning. And for the configuration of the NDT, we use the ETSI Teraflow SDN controller that was able to install the appropriate ACL rules. And that will be my presentation. I don't know if you have any questions, comments.